Okay, welcome back everyone for this last session. So what I'm going to cover here is some of the newer features in OpenMP. Well, some of these are not really emphasis on the newer rather than the really new in some cases. So we're going to look at some other things first, but then finish up with the GPU or accelerator offloading capabilities. But before that, let's look at some other things that are relatively new or that you might not have seen in OpenMP. So what happened in terms of the history? Okay, so version 4 is already more than 10 years old. So that was when the accelerator offloading was first added. Also some thread affinity things and some extra task support. So 4.5 didn't really add a great deal, but that's that's at least now available in most of the production compilers. And then we went on to, then we had version 5 in 2018. So some more features, some extensions to the offloading capability, new version of the memory model, and also kind of probably more importantly, updated the versions of C, C++, and Fortran that are supported as base languages. And then 5.1 and 5.2, mostly really fairly minor changes. What do you get in current compilers? Well, it's a bit of a mishmash really. So most of them are at least 4.5. Most of them are 5.0, and then whether you get 5.1 or 5.2 supported is still a bit kind of hit and miss with some of the implementations. Okay, so what feature I'm going to cover here? I'm going to talk about user-defined reductions, construct cancellation, portable SIMD directives, a couple of additional things to do with tasking, and the thread affinity features. Okay, so let's start off with user-defined reductions. So this was added in 4.0. So prior to that, you were not able to do reductions on objects or structures. You were restricted to doing it on basic types or arrays of basic types. But what you can do with the user-defined reductions is essentially allows you to define your own reduction operators, and then those new operators can be then used in a reduction clause in the normal way. So the syntax looks like this. It's hashtag OMP declare reduction, or Fortran $OMP declare reduction. Then we have the reduction identifier. So that's the name you're going to use as the operator in the reduction clause itself. A list of types to which the reduction can be applied. And then a code fragment which tells the runtime essentially how to combine two elements of this type in order to form the reduction. Because it's, it can then, as long as it knows how to combine two things, then it can combine arbitrarily many in a sort of iterative or recursive fashion. Then optionally, you can also specify the how to create the identity elements, so how to initialize the private copies of the types that are going to be created when at the start of the construct. Okay, yeah, so maybe said all this. Reduction identifier gives it a name. It can be overloaded for different types, and it can also be redefined in inner scopes as well. Yeah, everything else I think I've said. So yeah, the combiner is basically an expression that specifies how to combine the values, and we'll see how that works in a minute. Okay, So here's an example would be, okay, this is how to write a reduction operator that will merge or concatenate vectors from the STL in C++. So what you could do is you can declare your reduction. I'm going to call it merge. Let me get my pointer. Okay, so I'm going to give it the name merge. Okay, the type that it applies to, I can say, okay, it's going to apply to std vectors specialized on ints. And then I give the expression that says how to combine two things of these type. Okay, and in order to do this, there are two predefined variables. Okay, so they are omp out and omp in. Okay, so omp out is going to, so basically what we do is we're going to write code that combines omp out and omp in and produces omp out. Okay, so although you think, okay, it's going to overwrite one of the inputs with the result. So to merge vectors, what we can do is in omp out, we would insert at the end of omp out the elements starting from the beginning of omp in and going up to the end of omp in. So I'm going to concatenate the whole of omp in onto the end of omp out. So that gives me the method that defines the method for combining two elements. So once I've done that, then I can use merge as a reduction operator. So I can have a normal reduction clause that would just say reduction merge colon my vector, and then that all works. Can you control the order here? Can you control the order? You mean the order in which the reduction happens? No. No, you can't. Okay. It's yeah. But it's same. Yeah, so it's the same as for any other reduction operator. You don't know what order is going to be done in. That's up to the implementation. So typically for efficiency, reductions are done as tree operations and use a tree structure so that you can effectively do it in the log number of threads time rather than order number of threads time. So no, it's left entirely up to the implementation to determine the order in which things happen. Okay, so the next one is construct cancellation. So this is a clean way to signal early termination of code inside an OpenMP construct. Because for most OpenMP constructs, you're not allowed to arbitrarily jump out of them, because basically you're leaving the other threads executing, and once as soon as they reach a barrier somewhere, your code would just deadlock, because you've got a subset of threads arriving at the barrier. Any threads that have jumped out of the construct will never hit the barrier at the end. And it's the same with things like critical sections as well. You're not allowed to jump out of critical sections, because that would leave the lock acquired, and no other thread could ever get into the critical section. So this is provides you with an easy mechanism or a clean mechanism to be able to essentially not really jump out of an OpenMP construct, but jump to the end and cause all the other threads to jump to the end, at least not if not immediately, then as soon as possible. So the idea here is that inside one of the parallel construct or one of the another So you can use this. This works for parallel, for sections, for do or for in do in Fortran, for in C, or task group. Okay. So what happens is one thread is going to signal that they want to cancel the construct, and as soon as the other threads observe that signal, they will just stop what they're doing and jump to the end, and so will the signaling thread. So it looks like is $OMP cancel or hash pragma OMP cancel. Then you have to tell it which construct you're canceling. Okay, so whether it's the parallel region or the loop or the task group or the sections construct, and then you can also have a condition under which the signal will happen. And then, as well as the actual, so this does the signaling. You can also have indicate cancellation points in the code. So this is points where thread will check to see if the signal has been raised. There are implicit ones. So the cancel directive itself is also a cancellation point. Or whenever threads hit a barrier, that's also an implicit cancellation point where they will check to see whether the signal has been raised. So possible use case might be something where you are doing you want to do a parallel search, but you're only interested in finding the first occurrence of something. And then once you've found one occurrence of something in whatever you're searching for, you're done, and you want all the other threads to stop searching. So something you might do something like this. Okay, so you have a parallel loop, which for every iteration it does some test, and eventually it returns. One of these is going to return true, but as soon as you have as soon as the first thread that sees a true value here, then you want everybody else. You want to stop and say, okay, we're done. So we can do that with the cancellation construct. Okay, so let's have just say cancel the parallel region if Eureka is true. Okay, so the first thread for which it's true will hit this and raise the signal. All the other threads will then if they're still inside this testing, they will complete what they're doing in here. But as soon as they hit the cancel directive, that's also the cancellation point. So at that point, they will jump out and jump straight to the end of the parallel region. Okay, any questions about that? Okay, so next one is the portable SIMD directives. So a lot of compilers support their own set of SIMD directives to help the compiler to vectorize loops. In general, compilers can struggle to generate SIMD or vector code without some hints or without the programmer specifying some additional information about the code. The compiler can find it very difficult to determine whether it's safe to use vector instructions. So this is in some ways rather orthogonal to the rest of OpenMP because it's essentially, although it's a sort of parallelism, it's really not that well connected. It's kind of almost orthogonal to thread-based parallelism. However, it was, OpenMP, I think, was thought as a convenient place to standardize this stuff rather than create a completely separate standardization body and process for these things. It was, generally felt that it would be a good idea. Compilers all support similar features, but they all had their own syntax for it. So it would be a good idea to have some standardization here and make it portable. So the most important directive here is the SIMD directive, which indicates that a loop should be SIMDized. Okay, so it indicates that the compiler should generate vectorized instructions because the loop iterations are independent of each other. So this applies to a loop. So it looks like hash pragma OMP SIMD or $OMP SIMD in Fortran. So that says, okay, please execute the iterations of the following loop in SIMD chunks. So this does not of itself divide the loop across threads. Okay, you can combine it with a loop, a work sharing loop directive, but a SIMD directive on its own does not divide the work across the threads. So a SIMD chunk is just a set of iterations which are going to be executed concurrently by SIMD lanes using the vectorized instructions. Okay, and there's various clauses on the SIMD directive. So Ian asks, SIMD performance is tied to the ISA available. Does this also compile multiple ISA levels that can be selected at runtime? So does it do both AVX2 and AVX512? I think the answer is no. You would need to select at compile time using compiler flags as to which instruction set you wanted to target. Okay, so yeah, there's various clauses which controls the data environment and how the loop is partitioned and so on. In particular, so things you can specify are a safe length. Okay, so that puts an upper bound on the number of iterations in a SIMD chunk. One of the common obstacles to vectorization that compilers find difficult to deal with are so-called induction variables. Okay, so variables which are incremented by a constant amount in every iteration. So, formally the compiler sees that as a dependency, but it's relatively straightforward. If the compiler knows about them, if you tell the compiler what they are, then it can essentially reformat the code so that those variables are directly computed from the loop iterator rather than incremented every time. So it can be dealt with fairly straightforwardly. And another important thing is to be able to specify the byte alignments of variables. That's something that's another reason why compilers struggle to generate vectorized code in general cases, is because they cannot tell how arrays are aligned with respect to the vector lengths. And so you can this clause allows you to say, okay, I guarantee that this array element or the start of this array is aligned on a 32-byte or 64-byte boundary or whatever. So in general, compilers can't tell, particularly if these things are just passed as addresses into routines. There's no way that the compiler could possibly know what the alignment is. So you might know that you always pass this. That argument you are always passing the start of an array as an argument to some function, but there's no way that the compiler knows that. It has to assume the general case that you could be passing anything. You can also have last private, reduction, and collapse clauses on there that have their usual meanings. And there's also a declare SIMD directive, which allows you to generate or tells the compiler to generate vectorized versions of functions. Okay. So these essentially have to be, there's some restrictions obviously on the type of functions you can do with that. but so they essentially have to be pure functions where you're passing scalars in and scalars out, and it will generate versions which take a vector in and put a vector out. And then you can combine the SIMD directive with loop constructs. So you can have hash pragma OMP for SIMD or hash pragma OMP parallel for SIMD, so that that will both parallelize and vectorize the loop. But that's not necessarily always what you want. Sometimes if you've got a nest of loops, you might want to divide the outermost loop across threads, but vectorize the innermost one, for example. Okay. And there's a couple of other bits and pieces to do with tasks that I didn't mention yesterday. There is a task loop directive which provides a convenient way just to turn loop iterations into tasks. And, so otherwise you would just need to rewrite your loop in general. So Ian asks, how well does vectorized inner loop construct work? Do most processes have a vector unit per core, or will this possibly add resource contention? No, so typically every core has its own vector units. It probably has, may have more than one, or it may have, depends on the design of the processor. You either get a vector multiply unit and a vector add unit, or you might have one or more combined fused multiply add units. But that's all on the core. So it's it's just it's an extension to the it's in addition to the scalar floating point units. So the only way you could get contention is from hyperthreads or SMT. Okay, so because the hardware threads on the same core will share the vector units, as they do the normal scalar floating point units as well. So task loop just allows you to generate tasks from loops in a convenient way. So I mean, if you just wanted every loop iteration to be a task, then that's fairly straightforward. You just put the task construct around the loop body. But say often you want to choose, you don't want every single loop iteration to be a task. You want a set of loop iterations to be a task to keep the overheads reasonable. So you can say things like task loop with a grain size of 16. Okay, so grain size here is kind of the equivalent of chunk size for work sharing loops. So it says it'll take groups of 16 iterations and turn that into a task. So alternatively, you can also specify instead of the grain size, you can also specify the number of tasks that get generated from the loop instead. Okay, so basically it's just the other point of view. Okay, so the number of iterations in the loop will be the number of tasks times the grain size. So you can specify either one of those. So Ankit's asking, how does the task loop construct compare in efficiency with traditional task creation methods? It's basically the same. Okay, it's really just a convenience that prevents you from having to refactor your code. But really, it's the underlying mechanism for generating tasks is just the same. So I wouldn't expect this to really have any significant performance differences. It's really just a programming convenience. And another fun thing you can do with tasks is to specify dependencies. And so, by default, so all tasks are considered independent of each other and can be executed in any order. But not all algorithms are like that. Sometimes you have dependencies between tasks, and it may not be easy to express those dependencies with the task synchronization constructs like task wake or task group. And so the task construct takes a depend clause, and the dependencies are essentially expressed as on addresses. So, I mean, kind of the idea is that you are specifying the variables which those tasks are accessing. Okay, so if a task reads a variable, then you'd want that as an independency, and so that's something that previous tasks that write that thing should have completed first. Or if it's a write, then you probably want, that specifies that subsequent tasks that read it need to be executed afterwards. So that's the basic idea here. But actually, there doesn't have to be a mapping between the things you put in the dependency list and the actual variables that the task uses. I mean, it might make sense in some cases. In other cases, you can just create data structures which are simply used to express the task dependencies and which you never actually store any values in. Okay, so syntax looks like, type of dependency, which is either in or in-out, which is both, and then a list of variables. And the list can also contain subarrays. And so and it uses the syntax for subarrays. So OpenMP defines a syntax for specifying subarrays in C and C++. So you can use this. So this isn't the only place you can use them. You can also use that syntax for if arrays appear in private clauses or reduction clauses, for example. You can specify subarrays with this special syntax. So what do the dependencies actually mean? Okay, so the wording is the definition is a little bit complicated here to get our heads around. So of an independency, it says that the generated task, okay, so the task that's about to be generated will be a dependent task, so it must be executed after all previously generated sibling tasks that reference at least one of the list items as an out or in-out dependency. Okay, so dependencies only work between sibling tasks. So that means tasks at the same level of nesting. So there's no way you're not allowed to express dependencies between tasks at different levels of task nesting. It only works for siblings. And then, so as far as the dependencies are concerned, actually out and in-out are synonymous. You can just specify both to make the intent of your program clear, but they actually have the same semantics. So this says that the generated task will depend on all previously generated subtasks that reference at least one of the list items in any depend clause. So that's kind of a little bit obscure, but and it's possible to program quite complicated dependencies. You can effectively pretty much program any sort of dependency graph that you want to with a bit of care. There's just like a simple example here would be, okay, so I've got 3 tasks and the third one depends on values computed by the first two. So you could say, okay, first one have an out dependency on A, second one have an out dependency on B, and the third one have an independency on both A and B. Okay, so what that would mean would be that that allows these first two tasks to execute concurrently at the same time, because they don't depend on each other. But the third task has to wait for both of the previous tasks to complete before it can execute. So probably the main field where these kind of things have proved useful is for dense linear algebra operations. So if you're coding things like LU factorization or something like that, then and doing it in parallel, then you have several different types of operations there. So you have operations on columns and operations on blocks, and there are various the dependencies between them are not completely trivial. And if you write the code without tasks, then effectively you have to choose a certain ordering in which things are going to happen, which is more constraining than the actual data dependencies. But by using tasks, by turning it all into tasks with dependency clauses, then you can actually just only express the orderings which are really required by the data dependencies, and then let the runtime sort everything out, and allow tasks to run as the tasks to run as soon as they're ready, which is kind of difficult to do with conventional, using conventional loop parallelism, for example. Okay, and the last one is affinity control. Okay, so this is the ability to bind threads to cores or other hardware, other levels of the hardware hierarchy. So since a lot of systems now they are NUMA and also have SMT, so also have hardware threads. Then choosing where your threads are placed on the hardware can have a significant effect on performance. Well, that's certainly true as if we have nested parallel regions. That's when you start to really have to care about this kind of thing. For sort of flat one-level parallelism, then you probably don't care that much, as long as every thread has a different core, then you might not care that much. But in some cases you might care. If you're not using all the cores in the system, you might want to decide, are my threads all are my threads all running on the same NUMA region, or do I want them spread across different NUMA regions? And there are reasons for doing both. Okay, spreading them across NUMA regions would increase the available bandwidth, but it might also cause basically also increase memory latencies and reduce the amount of reuse in shared caches and so on. So it's not always, it depends on the application. It's not always obvious exactly what you want to do. But anyway, this is a mechanism that gives you the control. And the way this works is through increased number of options to the for the OMP proc bind environment variable. So you can still specify either true or false. Okay, so you just say proc bind equals true, and then leave it up to the runtime to decide on the mapping between threads and cores. But you can also provide a list, okay, with different possible values, which are master, close, and spread, to specify how to bind parallel regions at different nesting levels. Okay, so you can specify a different option for different levels of the nesting. And it also have a OMP places environment variable. So this allows you to say, okay, when you're doing this binding, what hardware entities are we talking about? So it could be threads, meaning hardware threads, or cores, or sockets. You can also give it explicit lists. So you can say, okay, I want you to, please bind my threads to cores 0, 4, 7, and 23. So exactly how those numbers are defined on the hardware, that's implementation defined. You need to read the documentation for the particular bus. Well, probably both the hardware and the OS that it's running. How it decides to number the entities in the hardware entities in your system. But you do at least potentially have that much control. Okay, so it's an example here. Okay, so suppose I have a code with 2 levels of nested parallel regions, and I want 4 threads for the outer parallel region, and then 2 threads for each of the inner ones. So actually, that's not right. Okay, this example has I've actually got 4 threads for each of the inner ones. So it should be OMP num threads equals 4, 4 here. Oh, sorry about that. And then we say, okay, how do we? So imagine I've got is some hardware, a chip that has 8 cores, say, and 4 hardware threads per core. Okay, so I could say, okay, the hardware entities I'm talking about here are the hardware threads, and the binding pattern I want is spread, close. So what that will do is so at the top level parallel region, it will spread the 4 threads out as far as possible apart from each other. So they will run on the top level threads will run on cores 0, 2, 4, and 6. And then close says, okay, for the next level down, I want you to keep it close to the master thread for that the generating thread for that parallel region. And in fact, there are kind of some rules about how all this works. But in this case, what you'd have is the 4 threads that are generated at the lower level. You would get them split over the 2 cores and use 2 hardware threads each. Okay, so yeah, there is some kind of specified algorithm as to how this all works. But and it's a little bit messy, but it potentially allows you to decide how your tree of threads is mapped onto your hardware hierarchy. So this is largely for supercomputers. This kind of stuff is largely irrelevant because the batch system is essentially taking care of the binding for you rather than having to do it through the OpenMP runtime mechanism. Well, actually, it's a collaboration. It turns out there really has to be some collaboration between the batch system, which is allocating the hardware resources, and the OpenMP runtime, which is generating the threads and deciding how to map your threads onto those hardware resources. So it can end up being a combination of both the operating system and the OpenMP runtime via the environment variables. So yeah, you have to typically read your documentation, read your system documentation carefully to figure out how the binding, because again, we're usually dealing with both MPI processes and OpenMP threads. So you have to figure out how the binding is done. Okay, any more questions about that? Okay, so the last thing we're going to talk about in this course is the capabilities for accelerator offloading from OpenMP. Again, this is a topic that probably deserves its own a whole course in its own right, but I'll at least cover the basics here. Okay, so a little bit about the background about the accelerator support in OpenMP. Okay, the way it was designed, and part of the reason why it took rather a long time to get it into OpenMP was that it was designed not to be GPU specific. So at the time when this was added to OpenMP, there was at least one other interesting device out there, which were the Intel Xeon Phis. So the design of OpenMP offloading was, something of a negotiation between Intel folks and everybody else, so to design something that would work sensibly for not only for GPUs but for other accelerator devices. But however, at the moment, at least as there are now serious competition between vendors for GPUs, at least between NVIDIA and AMD, and potentially Intel as well, if they can get their act together. So that makes using a portable API like OpenMP more attractive for applications than it has been in the past. The only other implementation that I know of is a bit of a niche one. So Texas Instruments have an offload implementation for their DSP chips, signal processing chips. So nice thing about the OpenMP offloading is that it's kind of fully integrated into the rest of OpenMP. It's been around for a while now, so it came in 4.0, but there were some revisions, and so some changes were made to how it works, as well as extending it in 4.5 and 5.0. Okay, so if you've come across OpenACC, then the OpenMP is similar in spirit to, but not the same as the OpenACC directives. So OpenACC is an alternative standard which uses directives that, in a very similar way to OpenMP, for offloading to GPUs, which was developed before OpenMP 4.0. These days, the functionality supported by OpenMP and OpenACC is pretty much the same. So anything you can do in one API, you can do in the other, more or less. They just spell stuff. They just spell their directives differently, and there's a few things. Things work slightly, syntactically slightly differently, but the functionality is pretty much equivalent. And so there's now quite a few reasonably stable, usable implementations of OpenMP for GPUs. So Cray compilers, NVIDIA compilers, IBM, LLVM, Clang, GCC, all have reasonable support for the offloading. Okay, so how does this work? So there's a bit of terminology to get through here. So the way that there's an underlying model that OpenMP works with here so it's a host-centric model. So that means that basically, your program starts executing on the host, in other words, the CPU device, and then it assumes that you've got exactly one host device and potentially multiple target devices, but the target devices are all the same. Okay, all the same type. So it doesn't support, OpenMP doesn't support heterogeneous devices attached to the same in the same node. So it assumes you've got one CPU or at least one shared memory node. So it could actually be multiple CPUs. That'd be fine. And it could be multiple sockets. And then you've got a number of GPUs, for example, but the GPUs are all the same. Okay. So what does it mean by device? So from the programming point of view, a device is a logical execution engine with some local storage. Okay, so it's something that's capable of executing code, but also has its own local memory attached to it. And the OpenMP specification also talks about the device data environment. So this is the data environment that's associated with one of these offloading clauses. So there are various constructs which control how both the data and the code is going to be offloaded to a device. And the data is mapped from the host data environment to the device data environment. So what does that mean? So it means that you refer to the variables with the same name, okay? But you have to specify when copies are made, when values are being copied from the version of those variables that's on the host to the version that's on the device and back again. So we refer to variables with the same name, but underlying that going on, there are separate copies of those things on the host and on the device. Okay, so start off by talking about the target region. So in the same kind of spirit as the parallel region is the basic parallelism construct in OpenMP, the target region is the basic offloading construct. So whenever you do any offload any code, it has to be via a target region. And similar to a parallel region, a target region defines a section of the program. And the model is that your OpenMP program starts executing on the host. And then when a target region is encountered, the code it contains will be executed on the device. And if we don't do anything else, then by default, the code inside the target region will just execute sequentially. So the target directive of itself does not specify how parallelism is going to work on the device. It just does the offloading. So it looks like hash pragma OMP target or exclamation mark $OMP target, and then a structured block of code. And in Fortran, you'd have the end target as well. Yeah, so the model looks like this. Okay, so we start off executing the sequential part of the program on the host device. When we get to a target region, then the body of the target region will be executed on the device. And by default, as far as the host is concerned, the target region is blocking. Okay, so the host thread will by default wait until the device has finished executing the code inside the target. Okay, there's ways to change that, but the default is synchronous and blocking. Okay. And then we can repeat that process as the program proceeds. Okay. So how is data dealt with? Well, the host and the device are assumed to have separate memory spaces. So in order to access data inside the target region, we have to have mapped it to the device. And to avoid any inconsistencies, then once data is mapped to the device, you're not allowed to access it on the host until the target region has completed. Okay, so during the target region, only the device is allowed to access the variables with that the variables with that name, and the host is not allowed to access them. So that prevents any. So that rule kind of prevents any inconsistencies in the values of those variables. So there is some default behavior here. So scalars and this kind of something that changed between 4.0 and 4.5, but so everything you're likely to see now is 4.5 or later compliant. So scalars that are referenced in the target construct are basically treated as first private, okay, by default. So you get a new copy on the device initialized with the value that the host has. So you automatically get a new copy with the current value in it. And by default, if you have static arrays, then they will be automatically copied on entry and back again. So you don't have to. So there's some default behavior you can use. You don't have to. You can always specify things explicitly. So in general, though, we want to control the data movement, and this is done by the map clause that appears on the target construct. Okay, so the map clause consists of a map type colon a list of variables. So the map type can be to, which means copy the data to the device on entry. From, which means copy that data back from the device to the host on exit. To from, which means both. Okay, copy on entry and back on exit. Or the final option is alloc, which says just allocate an uninitialized copy of this thing on the device, but don't actually copy any of the values. So if you don't need to copy values, you can just create a version of those variables on the device and avoid the cost of doing the copy. Okay. So start with a simple example. Okay, so suppose we have a loop like this, just forming the dot product of two arrays. Then we could specify, okay, what we want to do here is offload this code to the device. Okay, we're not saying anything about parallel execution yet, but let's just handle the data first. So let's say, okay, the arrays B and C need to be mapped to the device, but they're read-only, so they don't need to be copied back again because the device code is not going to change them. So we can have a map to clause for B and C. On the other hand, for sum, so we need both the initial value to get copied to the device, and we're going to do anything useful here. We also want the final value copied back again. So we would put sum in a map clause with a to from. So, but yeah, just to emphasize, this is still sequential execution on the device. So that's probably not very useful of its own, but it shows how to do how the data movement works. Okay. So for dynamically allocated data, then that works, but we need to specify the number of elements to be copied. Okay, and this is another case which uses for C and C++ uses the special OpenMP subarray syntax. So, example, if we have a pointer B and we malloc some amount of memory to it, then if we want to map that to the device, we have to say, okay, I have to tell it the starting element. Okay, say, okay, start from element 0 of this array and map n elements. So the syntax is slightly confusingly if you're bilingual. Okay, so the C and C++ syntax is the start colon the number of elements. So that's not the same as for the syntax for Fortran subarrays, which specifies the start colon the end. Okay, so that's not so nice if you are translating or familiar with both languages. That's a potential source of confusion. Okay. But this subarray syntax, you can also do parts of array. Okay, so I can say, okay, just map the 3 elements starting at B10. So particularly for GPUs, well, at least until the next generation of chips, which might have better support for unified memory. So current GPUs anyway, moving data between the host and device is expensive. And it's a reason why, that probably the main reason why only certain types of application can usefully make use of GPUs is because they're able to keep most of the data on the device and not keep having to move it back and forth between the CPU and the GPU. So that means that we'd like to avoid mapping the data in every target region if it's possible to, if it's correct and possible to keep the data on the device between target regions. So in order to do that, there are some other constructs. There's the target data constructs, which they just map the data, but don't offload any code. Okay. And then there are also target update constructs, which just do value copying. Okay, so once data has already been mapped, the target update just allows the copies of the data to be made in either direction. So typically where you'd use this is you'd say, okay, somewhere at the beginning of the code, before I do all my offloading, I'm going to map some data to the device. So I can do that, just map the data with target enter data. Okay, so that says at this point, I'm going to map these arrays A and B onto the device. And then, for example, so I might have a sequential loop. So maybe some sort of time stepping or iteration loop on the host, and every iteration of that loop has a target region in it that is going to do something with A and B. But also, there might also be some computation on the host going on in that loop as well. And then when I'm all done with this loop, then I say, okay, so maybe the result comes in, the result I'm interested in is now stored in B on the device. So at the end, once we're all done, then we can get the values of B back from the device with a target exit data. But between the enter and the exit, then these things are available on the device for any target region. And we don't have to map them explicitly on the target construct. And we can also just move bits of data around whenever we want to. So again, suppose we have a target enter data that maps A and B. Let's get my pointer up here. Okay, target enter data that's going to map A and B to the device. Then we have a target region that uses A and B, and then suppose we want just the first element. We want to do something with just the first element of A on the host. So we can use target update from to get the current value from the device back to the host, modify it, and then push the new value back to the device, and then carry on with other target regions doing more stuff with A and B. Okay. So you can imagine if you have perhaps an MPI application, then this is the kind of pattern you might want. You might, if you're doing halo exchanges, those would have to come. Those would typically have to be, your MPI calls would have to be on the host. So you might have this pattern where you do some computation on the device, you grab your halo data from the device back onto the host, you do some halo exchange in MPI, and then you push the received new values of your from your halo back to the device again, and then carry on computing. Okay, so that's essentially how all the data movement works. Then have to now carry about parallelism on the device. Okay, so in principle, we can use all the normal OpenMP constructs inside a target region to create and use threads. So we can use parallel regions and work sharing and synchronization and tasks and so on and so on. However, specifically for GPUs, they don't support a full threading model outside of a single stream multiprocessor. Okay, so GPUs consist internally of a number of stream multiprocessors, each of which internally supports multi-threaded execution. So there's this kind of two-level hierarchy inside of the hardware inside the GPU. But the way GPUs are designed is that it's essentially not possible to synchronize threads that are executing on different stream multiprocessors. So in particular, you can't have any synchronization. You also can't have any memory fences either. Okay, so there's no way to keep the data consistent between the SMs either. And in modern GPU designs, so older GPUs didn't have caches at all. Modern ones do tend to have caches, but they're not kept. The caches on different stream multiprocessors are not kept coherent. Okay, so there's no cache coherency mechanism going on. So what will happen is if you just put a parallel region inside a target region, that's only going to execute on a single stream multiprocessor. Okay, so if you're familiar with CUDA, then the same restrictions apply there. Effectively, in CUDA, you can only synchronize threads inside a thread block, which is executing on one SM, and not between thread blocks, which are executing on different SMs. So different APIs have to reflect this this restriction in different ways. Okay, so one stage better than sequential execution would be this. Okay, so we could just have the same OMP target and map target directive with map clauses as before, and then we can just annotate the loop here with a regular parallel for and a reduction clause. Okay, so in principle, on some other devices that might that support full shared memory, that might work fine, but on a GPU, that's not much use, because that's only going to use can only use one of the stream multiprocessors. What happens to N here? Should that not get mapped? N will be mapped as N will be treated as first private by default here, because it's a scalar variable referenced inside the in the actual code in the construct. So the default rules would apply here. So you'll get a private copy of N on the device and initialized with the value that it had on the host. But you could explicitly map it if you wanted to. It wouldn't hurt, but the defaults will take care of it. So in order to deal with this feature of GPUs of having multiple SMs, OpenMP has a teams construct. So what this does is that it effectively creates multiple master threads inside the target region. And then each of those master threads can in turn spawn its own team of threads with a parallel region, using a parallel region. Okay. But there is, in order to reflect the capabilities of the hardware, threads in different teams are not allowed to synchronize with each other. So things like barriers, critical regions, locks, and atomics only apply to the threads within a team. So we can, you have some control here. You can set the number of teams, query the current team ID, query the number of teams, for example. So just in the same way as you can set the number of threads in a parallel region, get the current thread ID, and ask and query the number of threads in the team. Okay. So basically, you have this hierarchical organization here. So what the code would look like, you would have a target directive followed by a teams directive followed by a parallel directive. So the target does the offload. The teams directive creates multiple master thread. Okay, so each team that we're going to create on the device has its own master thread, and then each team will use the parallel region, the conventional parallel region directive to create a team of threads. So each team will create its own separate parallel region. So the idea is clearly that different teams will get mapped to different SMs, and within an SM, the parallel region will spawn the threads that are going to execute inside that SM. So to help support that, and because the commonest thing we ever want to do with GPUs is accelerate loops, if we want to offload a parallel loop to the device, we'd probably want to distribute the iterations of the loop across the teams as well as across the threads within the teams. So OpenMP has a construct to do this, which is called distribute. Okay. So this behaves like the work sharing for construct, but instead it assigns iteration of the following loop to different teams. And analogously to the for construct, it has a schedule clause called dist schedule. But again, in order to respect the restrictions on the hardware, you can only have this can only be static with a chunk size. So you cannot do dynamic scheduling, dynamic loop scheduling across teams, because that would require some synchronization in the which the hardware does not support. And you can combine all these directives onto a single line. So in order to do anything really useful with this example, you actually need this slightly silly looking long directive. Okay, so it says OMP target teams distribute parallel for. Okay, so just remind you what all the different bits do. So the target does the offload, the teams creates multiple master threads, the distribute distributes the loop iterations across those master threads, the parallel creates a team of threads from all of those master threads, and the for distributes the loop iterations from that master thread across all the threads in the parallel region. So end up with this rather crazy construct to just to offload a loop to a GPU. So some other things. So if you want to call a function from inside a target region, then you have to tell the compiler to generate a version of that function or subroutine that is compiled for the device. So you have to add some, basically add these declare target directives around the functions that you, around the list of functions that you, around the declarations for the functions. It works slightly differently in Fortran, so I'm sorry I haven't shown the Fortran syntax here. Fortran is slightly different. The declare target goes inside the actual function itself, inside the subroutine itself, essentially at the top before any of the executable statements. But if you want to call the function from inside a target region, then you have to tell the compiler to compile a version of that function for the device. What else have we got? Okay, the target region can take a device clause, so that allows us to specify which device to offload to if there's more than one. Okay, so it's quite common now to see supercomputer nodes that maybe have 2 sockets of CPUs and 4 or 8 GPU devices in the node. Okay. So basically this just allows you to specify which device you want to offload to. Okay. So a useful pattern with OpenMP might be say, okay, well actually I want to, you could have a parallel region on the device and have a parallel region on the host and have a CPU thread per GPU, and then each CPU thread could separately and concurrently offload to a different GPU. Okay, so that might be a sensible way of coding for multiple GPUs. It's not the only way to do it by any means, but that might make some sense. Yeah, so I mentioned earlier that by default the host thread will block until the target region is completed. And you can change that behavior by putting a no wait on the target, no wait clause on the target. And if you do that, then what you're actually doing is from the host's point of view, you are changing the target region into a task. So then you can use task synchronization constructs like task wait to wait for completion of that what's now the asynchronous offload. However, you need to then take care that in this case, this is where you need to take care that the host doesn't access any mapped data before the target region completes. So if you do that, then it's not guaranteed as to which version you're going to get afterwards. Okay. So a few performance considerations. Yeah, mentioned before, transferring data between host and device is expensive. So you really need to work, in general, you need to work quite hard to minimize that as much as possible. So don't transfer anything that you don't actually need, and keep data on the device as far as possible. Other consideration is that GPUs have got lots of cores in them, so they need lots of threads to work efficiently. And that means that you need to expose a lot of parallelism, much more than from the CPU. So for efficient CPU execution, then you probably need up to tens of threads to fully utilize your CPU. But for GPUs, you probably need on the order of 1,000 or more, order of thousands of threads to fully utilize the GPU hardware. So in particular, this means that you often need to exploit parallelism from more than one loop in a nest. So this is a good example where the collapse clause that we talked about yesterday is very useful in order to extract as much parallelism as possible from loop nests to keep the GPU, all the GPU cores and threads busy. The other consideration is, or another performance consideration is down to memory layout. Okay, so and the way that threads access data. Okay, so if you think about it, if you for CPUs, having different threads accessing neighboring words of memory is essentially a bad idea, because that's where you have a risk of false sharing. Okay, it doesn't matter if it's just reads, but as soon as any of those operations are write operations, you run the risk of triggering the cache coherency mechanism and having false sharing, like as we talked about yesterday. On the other hand, for GPUs, having different threads accessing neighboring words in memory can actually be good, because it's there's no cache coherency to cause any problems, and it actually allows the loading and it allows more efficient loading and storing of data if neighboring elements are all being accessed at the same time by different threads. So those kind of considerations conflict with each other, or can do. Okay, so if your data structures are being used on both the CPU and the GPU, you may be best to actually explicitly change the layout. So you might actually need to transpose your multidimensional arrays before mapping them to the GPU, or you might be able to take care of this problem by interchanging the loops, or using making sure that on the GPU you always use a static one schedule to get so that neighboring threads execute consecutive loop. Neighboring loop iterations are executed by different threads. And actually, some GPU implementations of OpenMP will actually choose a static one schedule by default for the GPU for this reason. Okay, that is the end of this talk, and that was the last the taught sessions for this course. So does anybody have any questions about that? Do you need anything special when compiling other than G++? You might need another flag to specify what sort of device you're compiling for. But apart from that, no. Should just work. I mean, clearly you need a offload enabled installation of the GNU compilers, which you may or may not have. Yeah. So just because GNU compilers are on the system doesn't necessarily mean they're offload capable. Example, okay. Anyone done hybrid offloading? I'm not sure what you hybrid between what, Matt? Not sure what you mean. MPI, OpenMP, GPU. Yeah, sure, no problem. Yeah, can be done. Though I think probably what you see more of is just MPI plus GPU. and not necessarily using CPU threads as well. But in principle, there's no reason why you couldn't do that. So dependent says, for example, which compiler? Okay, yeah, what I meant was that your normal or your normal installation of GCC may not have the offload capability enabled in it. So depending on what system you're on, if you want to use GNU compilers to do offloading, the system installed GCC or G++ may not have that capability, and you might need to install it yourself. Which I'm told is somewhat less painful than it used to be. Okay, it used to be really horrible and difficult install, but I'm told that these days it's the most recent versions of GCC are somewhat better. But if you're working with if it's NVIDIA GPUs, then the NVIDIA compilers have quite a pretty good implementation of OpenMP in them these days. Yeah, PGI compiler should work. Yeah, no problem. So I'm not exactly sure what compilers we're going to support or going to be supported for the upcoming test GPU system on ARCHER2. That's their AMD GPUs. There'll definitely be Cray compiler can target those, but I'm not sure if we're going to. I'm not sure what other compilers we might support for that. Thank you, William. Yeah, that was the extra flag that I was thinking of and couldn't remember. So I know William's had the pleasure of doing a GCC build with the offloading. So maybe he can comment on how unpleasant it is or not, or otherwise.
I can say when I was doing it in February last year, I didn't enjoy it at all.
Ha! Right. Okay.
Maybe it's got better since then.
Maybe it still is painful then.
It was these extra steps because I found I had to download GCC and then I think 2 extra bits of software to enable the targeting of the NVIDIA hardware, which you then had to tell GCC how to find and then build both the target, the device compiler and the host compiler separately, which was a little bit of a faff, but got there eventually.
Yeah, so it's yeah. it's not, shall we say, just not entirely straightforward. Yeah. In the past, I've built Clang compiler with offloading support, and that was kind of similar. You have to basically, download Clang, download the additional libraries, and then build it once, and then tell it where the libraries are, and then build it again, and then it still doesn't work. That kind of thing. Okay, any other questions?
I can maybe also quickly comment, since you mentioned ARCHER2, that I've been doing a little bit of testing there and found that I think, yeah, the Cray and AMD compilers seem to be very well set up for OpenMP offloading, and I think the only thing that's needed is the FOpenMP flag itself, and the compiler wrappers handle absolutely everything else. GCC, I'm still trying to work out. I'm not sure that that's in as good a spot.
Oh, well, that's good. So at least we'll have two options anyway.
Yep, they both seem really good, I think. So should
Okay,
be nice to mess around with those.
Yeah. Okay, so in that case, suggest we take a break in a moment. So I'd be most grateful if you would fill in a feedback form for this course. Doesn't take very long, promise. It's always very helpful to help us improve these courses going forward, and also to know what other things you might what other things you might be interested in from ARCHER2 training point of view. So okay, you can find the feedback form on the course web page, but I'll also just paste the direct link in here into the chat window for you. So yeah, take a break now, and I'll be around between. I'll be back at 4 o'clock. I'll be around for another hour or so. If anybody wants any other help with practical sessions, we want to finish them off, or if you want to ask me anything else that that I potentially might be able to help with, very happy. But on the other hand, if I've managed to fill your brain with stuff enough for 2 days, then please feel no obligation to hang around for the rest of the day. But I hope the course has been in some way useful for you. Okay, that's us at the end of the session now. So just want to say thank you very much for coming along to this course. Hope it was useful for you, and thank you for asking so many interesting questions. Don't forget, please, to fill in the feedback form if you haven't already done so.